In this video, I will show yet another wrong proof of Q, the set of rational numbers, being a field. But before that, I will review one of the properties of any fields. So this is a theorem actually. Let F be a field, any field. Then, first, we have for all elements of F, we have F times 0 is equal to 0, where 0 here is the 0 element of F. Remember, the 0 element of a field means that it is the additive identity. Okay? If you add 0 to any element, that element doesn't change. Okay, second, for all pairs of elements, say HK of F, if H times K is equal to 0, then H is 0 or K is 0. Okay, of course, both can be 0 at the same time, but the point is at least one of them should be 0 if their product is 0. Okay, I don't give the proof of this theorem, but just accept that for the moment. So here's a wrong proof. Okay, we want to prove that Q is a field, right? So for all elements of Q, that is for any rational numbers, we have Q times 0 is equal to 0, of course. And for any pairs of rational numbers, if P times Q is equal to 0, then P is 0 or Q is 0. Therefore, Q is a field. Done. And, of course, this proof is wrong. So why is that? It seems like we have used this theorem, but look, this theorem says if F is a field, then these two properties hold. Okay, not vice versa. So let's make it more formal. So let's say P, capital P, is a logical proposition that F is a field. And let Q be a logical proposition that 1 and 2 hold. Okay, 1 and 2 means these two conditions. Okay, so then the theorem says if P is true, then Q is true. But that does not mean if Q is true, then P is true. Okay, as we have learned in formal logic, the converse may not be true, even if the original proposition is true. Okay, so this does not imply the converse. But in this wrong proof, we are actually using the converse of the theorem. So of course, for any rational numbers, we have this and this, but it doesn't mean that it doesn't necessarily imply that the set of rational numbers is a field. To begin with, what is this 0? You know, for 0 to exist, we must know that this set rational numbers has a 0 element, right? But we haven't proved it yet. And so, in fact, since this is wrong, we can actually find an example of a set that is not a field, but satisfies these two properties. One example is the set of integers. Okay. For any integers, let's say x, of course we have x times 0 is equal to 0. And 0, this here means just integer 0, right? And for any pairs of integers, if x times y is equal to 0, then x is 0 or y is 0. In other words, if neither x and y, neither x nor y is 0, then the product cannot be 0. Okay, the same thing. But as we know this set of integers is not a field. Why is that? Because, for example, 2 is an integer, and it's not 0, of course, but we don't have its inverse, its multiplicative inverse. 2 inverse should satisfy this equation, but if this is true, then the multiplicative inverse of 2 should be 1/2, which is not an integer. So clearly, this is not a field, but still satisfies these two properties. So if it's not a field, then what is it? Actually, it is called a ring. And in particular, it is a ring. By the way, ring is a set equipped with addition and multiplication, but it doesn't have to satisfy the axiom of the existence of multiplicative inverse. Okay, so such a set is called a ring. And in particular, integer is a special type of rings called integral domain. An integral domain is a ring that satisfies this property. Okay, if the product of two elements is equal to 0, then at least one of the elements is 0. Okay, so field is actually a special case of integral domain. So in a sense, it is a subset of integral domain. Which is a special case of ring. Okay, so rings are more general. Integral domains are a little bit more specialized, and fields are even more specialized. Okay, so to summarize, what we have learned here is that you cannot always use the converse of a theorem. So if a theorem says if P then Q, you cannot use the converse in general. Okay? Even if this is true, it may not be true that if Q then P. Okay? So be careful.